share this. Okay, we'll share. Got it. And I'll share this one. Okay, you should see a green screen.
We do. Yeah.
And then I will click here. Now you should see my
Yeah.
screen.
Excellent.
Okay.
Yeah. Cool.
Well, good afternoon, everyone, and welcome to Promises and Perils of Artificial Intelligence. Last time we met, that was on Tuesday, we talked about, well, actually, it was a repeat of my talk that I gave last week at an optometrist kind of meeting. But it fits well. Last time, what I was trying to convey is that we shouldn't fear technology. We shouldn't fear AI. We should embrace it and actually use it as a tool to improve what we do already and do things that we were not able to do. So basically, it's something that is going to help us. So we should embrace it. That's the message that I tried to convey. I also tried to place where AI is. So vis-a-vis other terms, like we talk about AI, we talk about machine learning, we talk about deep learning, and people think it's the same thing. It is not. So artificial intelligence also is not new. It has been around for a very long time, since the 50s, so just after the Second World War. But it evolved significantly. And machine learning is a subfield within artificial intelligence. It became prominent in the 80s, and some applications were already very successful. But what changed everything was in 2012 when people realized that this forgotten technology called artificial neural networks, now called deep learning, can do amazing things, and even things that are surpassing the human specialists. But it's based on artificial neural networks. Okay, so what you need to remember is that deep learning is part of machine learning, which is part of AI. They're not synonymous. What we didn't talk about last time is the fact that there's a resurgence of AI recently. And why? Why is that? We said that AI has been around for a very long time, since the 50s. So why is it that everybody is now focused on AI and we are talking about it? It has to do with three factors. First of all, we have amassed an amazing quantity of data. We have a lot of data, more data than we ever had before. Every year we have even more data than we ever had before. And this data is very important in order to build the systems that we have today. The other thing that is very, the important factor that contributed to the resurgence of AI is the fact that our computers today are very, very powerful, and there's an improvement, almost an exponential improvement of the hardware. What you have in your pocket, the cell phone that you have in your pocket, is more powerful than many of the mainframes that were used. Actually, there was an embargo. You couldn't even sell it to some countries and things like that. Well, today you have it in your pocket. And that is very important, because now we can do incredible calculations that we were not able to do before. And some of these amazing algorithms some of them we developed a long time ago, but we couldn't push them to their limit because of the hardware we had. Today we have these amazing computers, so we can actually imagine new architectures for these algorithms, and we can do amazing things. So that's the reason why it's coming back now. So what can we do with this? And remember, I talked about machine learning and supervised machine learning. And I showed you this drawing where you have some data that is labeled, and the algorithm, the supervised learning algorithm, will go through this training data to learn a cloud. I represent it as a cloud, but actually it is a predictive model or classification model. I put a face on it, and then I use that predictive model to predict the labels automatically of instances that haven't been seen before. And that's what a supervised machine learning is. And we can use it in many, many applications, this idea. And I showed you some examples last time. I'll show you some other examples. So deep learning is one possibility to represent this what I showed you as a cloud. Okay, so we can use it in precision health. What is precision health? Well, basically, I'm trying to treat people differently depending upon their different cases. Each person is different. Today, we treat people based on the symptoms that they have, but not necessarily based on their characteristics. Everybody who has the same symptoms will be treated with the same kind of medicine, same kind of treatment, even though these people are different. The idea is that I can divide these people in different cohorts, and based on their characteristics, not just the symptoms, I can treat them differently. And that's what we call personalized treatment or personalized medicine. So I am adapting it to different individuals. And machine learning can help me do that. Not just treatments, diagnostic, prognosis, and all these things can be done using machine learning. And often people think, well, to do this, you need to have the genes of the patient, and it's based on the genome and all this stuff. It's not necessarily based on SNPs or gene expressions or even metabolomics. It can go beyond that. Any actually data can be used to do some personalized medicine. And I'll just show you some example. Here you have a new novel patient, and you want to know if for this particular patient, they will have a reoccurrence of a particular disease. Well, for this patient, you have many different characteristics in the health record or medical record. Well, you have also data about other patients. And the historical data about the other patients, whatever this information is, you have also in the record whether for these patients, the disease has reoccurred or not. And what you want to do, you want to predict whether for this particular patient, this will reoccur or not. Well, I can use the historical data to build this classifier. You remember this cloud here, a predictive model, and I will use this predictive model and I'll feed it with the characteristics of this novel patient to predict whether this disease will reoccur or not. Okay, this is exactly what machine learning is doing. So this has been used for many cases. I'll show you some cases that the U of A was involved in. This is the case of predicting whether a patient is ER positive or ER negative. So this is for breast cancer treatment, and is to decide whether to do an adjuvant treatment after the chemotherapy, yes or no, and with what kind of medicine. So we can, from the biopsy, we can do gene expression with the DNA microarray data analysis, and you extract these gene expressions, and you have information from other patients that you for whom you know whether they are ER positive or ER negative, and you build a classifier. And with that classifier, you will use the information for this patient from this biopsy, and you will determine whether they are ER positive or negative. And with that, you can decide whether you will treat them with tamoxifen or not. So this is personalized medicine again. And this has been demonstrated to be more accurate than the current techniques that we use, which is the immunohistochemistry, IHC. So it's more accurate. And this technique can be used for breast cancer, predicting whether this patient will develop some breast cancer, predict if the breast cancer will reoccur or not. For kidney transplant, you can predict whether the transplant will be rejected or not. So the new organ will be rejected or not. For prostate cancer, you can predict the toxicity level for a particular patient before even you do the radiotherapy, and so forth. And we can use, indeed, gene expression. You can use single nucleotide polymorphism. So these are what we call SNPs. But it doesn't have to be, as I said before, this kind of information. I'll show you another example where I think I talked about it last time. This is the case of detecting diabetic retinopathy and grading each case automatically. So basically we have images that have been graded. This is level 0, level 1, level 2, level 3. And we use that to build a predictive model. And that predictive model, given some images, will tell me whether it is grade 1, 2, or 3. But at the same time, we have another data set that is also labeled, but at the pixel level. And then we learn another model, and that model will feed the information to the other models. So this is what we call transfer learning. And in addition to predicting whether it's grade 1, 2, 3, or 0, it'll actually tell me in which region there are issues that made it decide that it should be grade 3 or grade whatever. So I can have now explanations of the prediction. Another example where machine learning can be used, this is using metabolomics. This is the case of, I believe, urine test. So you take a sample of urine and you can do the nuclear magnetic resonance spectroscopy. And with that information, you can build a classifier. And with that classifier, you can predict different things. In this case, we are predicting decaxia, so whether the person will lose muscle mass or not. But you can use the same technique for predicting different things and even recommending which treatment to use and so forth. So this is not speculation. This has been done and published to show feasibility. I'm going to skip this. This is the case of generating for diabetes. This is another example. This is to show you that we're not just using gene expressions and SNPs. We can do anything. I mean, we can use any kind of data. This is a case with the these are people who are workers' compensation board. These are people who are injured at work, and they are treated by the workers' compensation board clinics. And when people are injured, they go there, they get a treatment, they're first checked, and then they're given a treatment. After the treatment, they are evaluated to see whether they should go back to work or not. Because the purpose is to get them back on their feet as soon as possible, healthy, and also going back to work. But at the evaluation, we see if they're not sufficiently fine. Well, we have to prescribe a secondary treatment, and then afterwards we do another evaluation, and this can be iterated until they're fine and send them to work. We don't want this iteration to be very long. Unfortunately, it happens very often, and it costs a lot of money, and it's not good for the patients. So we looked at the cases that were actually good, where the treatment, what does it mean that we actually given a secondary treatment, a tertiary treatment, and so forth? It means maybe the first treatment wasn't the right one. So we look at cases that are short, where the treatment is actually working from the beginning, and we learn from there a classifier that will give recommendation to the evaluator which treatment to give. And the goal is to, so this is when we build the classifier, the goal is to give the appropriate treatment from the beginning. And indeed, we were able to reduce the cycle significantly. Another example where we don't use any genome or anything like that, but we use machine learning, and it's amazingly useful. This is the case of segmenting the brain images before surgery or before radiotherapy or something like that. But typically this is before surgery. And the doctor uses the 32 slices of the brain to do a segmentation in volume, so in space. And it's very tedious. They have very sophisticated tools to do that. And it takes about 20 to 30 minutes to do the job. It's a very long time. So we use machine learning to learn how to do this segmentation automatically. Okay, so now it's not to replace the human, but instead of providing the images unsegmented to the doctor, and then they have to segment it in 20 or 30 minutes, we provide the images pre-segmented by the computer automatically, and then the surgeon will only adjust these segmentations left and right here and there, and it takes 5 minutes instead of 30 minutes. So they save a lot of time. And this is thanks to machine learning. Machine learning learns from data that is provided, that these are patients that have been segmented in the past. Okay. Another example where machine learning is used in this particular case is in text. So in text, we're trying to determine the emotions that people have expressed while writing some documents. And this can be used for detecting mental health, for example, issues. I'm not going to go into details, but this is just to show you that we can use other sources of data, not just gene expressions. Okay. And to deal with, so this was published in 2019, to deal with precision health. Okay. Anyway, so it's obviously amazingly useful to society. These are examples in medicine. There are many other examples not in medicine, but I hope this is convincing enough. And but people are still alarmed and saying, well, even actually, I think I copy and pasted it. I put it in one of my slides. That's probably later. In the Globe and Mail today in the Globe and Mail, there's somebody who wrote an article saying that, AI is dangerous. Okay. Many people are alarmed. Okay. It says these machines are against us. They will eliminate us. There are issues with privacy, of course. That is obvious as well, and we have to be extremely careful. But let me show you the power that we have at hand that actually we're not using, which is very unfortunate. And I'm talking about medicine here. Imagine you have you go to a store, an e-commerce online store, and most of you buy things online. Companies online, they want to know more about you, so that once they know your habits and know how you behave, they will target you with the right advertisement so that you can buy more. They want to influence your behavior, obviously, for the purpose of making money. So because they're making money with that, they are investing a lot of money in order to exploit AI as much as possible to better understand your behavior. So they're talking about the customer DNA. Imagine this is the customer DNA. So now I go to the website, and in the website, I will register. Okay, so when I register, I may give some information like where I live, my name, my phone number, birth date, and so forth. And for me, and assume that's information that I volunteered and I gave them that. That's what they know about me. That's it. They don't know more than that. But actually, as soon as I start buying things, a watch, goggles, they already guess things. Oh, this guy likes swimming. Helmets. Oh, he does. He bikes. I may buy a coffee machine. They think I like coffee. Actually, I don't. I bought it for the wedding of some friend, whatever. But in addition to my activity, I also have a behavior. I may review products. I may recommend some products. I talk to friends if the system has some social media connections. I may do searches. I search about home improvements, and that tells them something. So it creates some kind of profile. In addition to the information that I gave them, my activity on the website and my behavior on the website, they can even look at web sources. So they can do automatic searches. They can find me on social media. They see what I like, what I don't like, what I talk about. They may tweet me, and they may even see the places I go to with geolocation. They may know more about my job, my colleagues. Um, um, Foursquare is to identify where the places where I went to. They may even search search engines, and they may find the images that I posted, articles that I may have edited on Wikipedia, the blogs, the text. So that showed you the example of mining the text to better understand the emotions and the mental health state of a patient. Well, they can do the same thing, and they can know about my emotions in time, things that I don't even know about myself. Um, so it's incredible what they can do today, and they do that already. Okay, um, uh, because there's a lot of money at stake. That's why they invest money to do this. But imagine if we were able to do it for our own good in medicine. So here's the DNA, not of the customer, the DNA of the patient, let's say. And when we may add generic data like the gender, the name, the age, the ethnicity. We may add historical data from the electronic health record or the electronic medical record. Well, it's not electronic, but it's still on paper, a lot of it, but it's being digitized. Um, you can add the prescriptions that you got in the past, all the information about the medical images, X-rays, MRI, fMRI, and so forth. In addition, all the lab results for the blood tests and urine tests and whatever, you name it. But you also can put genetic information, microarray data, SNPs, microbiome, metabolomics, and so forth. And then you can do other sources like many of us have these smartphones or other devices we have at home to measure blood pressure or sugar level or the different kind of sensors that can be also added in the database. Different activities that we do when we go running and so forth. And also what we write. So we can have also where we went in addition to our emotions. Well, if we have all that information, can you imagine, rather than getting these ads sent to us that are personalized ads between quotes, we can have personalized treatment or personalized advice what to do before we get sick. We don't want to get sick. So preventive kind of medicine, we will have an incredible power, like these big companies have power over us. Anyway, so this leads me to the achievements that, and unfortunately, by the way, this doesn't exist. We don't have it because we have many hurdles due to privacy issues and ethical issues. It's not an easy question to answer. I mean, there were some researchers that did work on checking the opinions of patients and their willingness to share their information. The conclusion was that when you ask a patient who needs help now, if you go to the hospital and you ask a person at the hospital, can we use your data to do research? And they will be surprised and say, yeah, of course, you're not doing that already. Of course you can use that because you're going to help me. Okay. And they're willing to share the information. But if you ask the same patient a few years later, can we use your data from 5 years ago when you went to the hospital? They will say, no way. So what is right, what is wrong here is not trivial. Anyways, the achievements, we achieved already incredible things in using AI. I'll start a little bit back here in 1997. That's when Deep Blue, a computer from IBM designed specifically to play chess, crushed Garry Kasparov. That was a big deal. And when that happened, I mean, go back to the archives, you'll see all the newspapers were talking about AI taking our place and we're doomed. But we did other things. Something that wasn't, I mean, an event that wasn't as covered as the game between Garry Kasparov and Deep Blue is Chinook. This was developed here at the University of Alberta, and Chinook beat the best player in checkers at that time, Marion Tinsley. But it's not just in one game; it was the whole tournament, and it won. It's the right to actually play the finals. That was in 1994, and in 2007 we solved the game checker. You cannot play checker against the computer and hope to win anymore. Even the best of the best cannot do that because we know all the possibilities has been solved. In 2011. IBM with their computer Watson, they had this game on TV where they beat the best of the best at the game Jeopardy. And that was, again, a turning point where everybody was talking about AI, and that's it. We are doomed, and AI will take our place. I mean, that was already 12 years ago. We're still here. Also, self-driving cars. Now everybody is familiar with self-driving cars, but it started in 95, where we had a car that was able to, on its own, cross the United States from Pittsburgh to San Diego. So from the east to the west. That was impressive. Here again at the University of Alberta, we have a program that beats professionals at the poker game. So the heads-up limit Texas Hold'em, and that was solved. And then the no limit version, we actually beat professionals. That's also very impressive. Recently, you all heard of ChatGPT, and yet again, the spotlight is on AI, and that's it. AI is taking over. That's why we had this article, as I said, today in the Globe and Mail. But in reality, it goes up and down. You have a big event like Deep Blue here, and there's a lot of hype, enthusiasm about AI, and then it fades out, and then another event, and then it fades out, another event. Recently, we had GPT-2 in 2019, and very recently ChatGPT, and again, you have this hype. But it's this phenomenon going up and down. What did I add recently? This morning, I added. So everybody heard of ChatGPT, I'm guessing, and everybody among you guys, everybody has tried ChatGPT, didn't you? I'm seeing some people that I can see nodding and saying yes. ChatGPT, the only reason you heard of it is because it was made public at the end of November of 2022. But these language models have been around for some time already. And each time they become bigger and bigger and bigger, and you guys don't hear about them until they're made public. So OpenAI, the company that built ChatGPT, made it public, and it was an incredible phenomenon, actually. But there are many here, some examples of evolutions of a language model. So what is a language model? Is actually a neural network, okay, that is designed specifically to find the associations between words in a very large corpus, and this is what it represents in the network. And it learns to predict what is the next word given a sequence of words. So if you prompt it with some words, it can predict the next word. And then now I have more words, I can predict the next one, I can predict the next one, and so forth, until I predict the end. And when you ask it a question, the words in the question are the prompt for the first word that it will generate. But the bigger the network is, the better it gets at memorizing these associations between words in their large corpus. We're talking about billions of documents, and the better it gets at predicting the word that will come next. And here you can see the sizes. This is in millions, so 340 million, we call them parameters, inside the network. And now we are talking about 530 billion parameters. That's phenomenal. The human brain contains an average of 90 billion neurons. Some people talk about 100 billion neurons, and certainly trillion synapses, these connections. The next generation of GPT, so ChatGPT is based on GPT 3.5, and the new GPT-4 is coming out this year probably, and people are estimating, speculating that it'll have 100 trillion parameters, so it's even more than the brain. So it's, but what people don't tell you, to build such a network, like for example ChatGPT, you require just for the infrastructure, just to buy the infrastructure, the machines, it's about $100 million. And then you need about $40 million to train this network, because you need electricity, you need cooling, because it's getting too hot. It's very expensive, and it takes months. So it's not at the reach of everybody. I have another figure showing you the different networks that exist. So ChatGPT is based on GPT-3, so it's based on GPT-3, but IBM has, not IBM, this is Google. Google has its own, and probably you heard last year, or was it the year before, one of the engineers tweeted that Lambda was becoming sentient, and this guy was fired from Google, and it was covered by the media. So Google doesn't want to make it public like OpenAI did with ChatGPT, but Lambda is actually even more powerful than ChatGPT. The problem with these, and actually I'll show you another graph, I think I have it here. Yes, this is the interesting thing. If you look at all the different tools that exist online, and how long it took them to get 1 million user. For example, Netflix, it took them 3.5 years to get 1 million users. Twitter took them 2 years. Spotify, 5 months to get the first 1 million users. ChatGPT, 5 days. In 5 days, we had 1 million users, and that's why everybody heard of it, and everybody was fascinated by this thing. But what we need to know is that, unlike Siri and Alexa, ChatGPT doesn't use the internet to locate answers. Instead, it constructs a sentence word by word, as I said before, selecting the most likely token or likely word that should come next. Based on the corpus that it visited. So these language models, they all work more or less the same way, but they hallucinate. This is the term we use. Hallucinate, it means that it doesn't necessarily tell you something that is true. They can fail at basic math. They can answer, sometimes they can't answer simple logic questions because they do not reason. There's no reasoning. It's all based on probabilities, basically. But they are very confident, even when they give you, they write plausible sounding, but incorrect and nonsensical answers. And because it sounds so confident, you trust it. But there are many cases where the facts that they claim are actually wrong. You can find online many of those examples. But anyways, this doesn't stop people from panicking and talking about the huge risk. And this is not new, of course. People like even Stephen Hawking was talking about the danger of AI that can threaten humankind. and people like Elon Musk and Bill Gates and so forth, they have said the same thing. But well, they're not completely wrong, but they're not right either. And people have retracted what they said in the past. Here's an example of what Stephen Hawking has said. It said, well, basically, it's not the AI itself that is dangerous; is how we share the wealth that is obtained thanks to AI, and that's the danger. So basically, capitalism is a danger to us for us. Okay, so let me tell you one story very quickly. This is the story of AlphaGo. Do you know about AlphaGo? Anyone who doesn't know about AlphaGo? You see, that's interesting because when AlphaGo was released, and actually when it became public, it was a big, big, big deal. Everybody knew about it, like you guys know about ChatGPT. And a few years later, well, you don't even know about AlphaGo, which is kind of interesting. So it's like Watson. Some of your guys may not even know about Watson that I mentioned beating the best of the best at Jeopardy. But at that time when it happened, it was a big, big deal, and this confirms the waves that I'm talking about. You have the huge hype, and then it disappears, it fades away. Well, in 2016, no, way before 2016. This is in 2012 or something like that. Anyways, David Silver, a student, an Australian student, came to work here at the University of Alberta for a PhD with Rich Sutton and Martin Miller. He was very interested in writing a program to play the game Go. The game Go, unlike checker and chess, was very difficult. Actually, it's a very simple game. It's a board game that is very popular in Asia. It's very simple, and even kids play it, but it was very difficult to write a program that can basically challenge humans. And David Silver wanted to work on something more sophisticated than what existed. So Martin is a specialist in Go. Actually, he's a strong player at Go himself, and he works on heuristic search and planning, while Rich Sutton works on reinforcement learning. And he finished his PhD, and he built a program that indeed was able to beat some humans, but not the experts. And when he finished, he was hired by a company called DeepMind, a small startup in the UK, and that company didn't have a product per se. They were working specifically on trying to solve what we call the artificial general intelligence. So something that is as intelligent as humans, and it will now solve all our problems. So when they hired him, they said, okay, work on something that you know and try to make it better. He became the lead of this research group called AlphaGo. And AlphaGo, because they have more resources than the university, obviously, AlphaGo became even better than the program that he wrote originally. And it happens that in 2013 or 2014, Google acquired DeepMind. Google acquired DeepMind because they were very interested, and this is in a TED Talk. Larry Page, one of the founders of Google, confided that the reason why Google bought DeepMind is because they have this amazing program that can not do just one thing. Like remember Deep Blue that beat Garry Kasparov? It can only play chess. That's it. And another program like Chinook can only play checker. That's it. But we humans are very versatile. We can do many things. I can play chess and checker at the same time. So they were fascinated by this program that some guys at DeepMind did that can play different Atari games at the same time, and they do it better than humans. And the interesting thing is that this program that was done also at DeepMind was also from students from the University of Alberta that were hired by DeepMind in London. Anyways, now DeepMind is owned by Google, and they have all the resources of Google, so they improved AlphaGo very much. And in 2016, they dared to challenge Lee Sedol, who is one of the best players of Go. He was a champion for 8 years or something like that, or 18 times actually world champion. And AlphaGo beat Lee Sedol. That was a big deal in the world, because a few years before that, no program was able to beat a child at the Go game, let alone a world champion. So that was an incredible improvement, very fast improvement. It shocked the world, except the Chinese. The Chinese said, it's not a big deal. We have a champion. Our champion, KG, is the current champion, and you can't beat him. So AlphaGo actually challenged KG, and KG was crushed. And you have news like these, like AI versus. Oh no, this came after. This came after. Of course, the news were all over this defeat by KG and how AlphaGo beat the best human. And then the interesting thing is that DeepMind didn't stop there. DeepMind said, okay, we trained this AlphaGo using all the games that we know that have been recorded that humans have played. What if we remove all this? We only give AlphaGo the rules of the game, and we let AlphaGo play against itself. And after a few hours or a few days, it learned more games against itself than all the games played by humankind in the human history. So, and they called this AlphaGo Zero, and they played AlphaGo Zero against AlphaGo, and AlphaGo Zero beat AlphaGo, which beat the human. So that was another shock. And it didn't stop there, because, and this was trained in 40, a few days, in 40 days. It's phenomenal. And then they said, okay, let's remove the rules of the game Go and put the rules of the game chess. What if we let AlphaGo Zero play against itself chess? Will it also learn? And indeed, it learned by itself how to play chess, and they put it against the best program, because the humans are already beaten by the computers. So they took the best computer chess game at that time, and they put it against AlphaGo Zero that learned by itself how to play chess, and it was 0 to 100 game. I mean, it's crazy. It was really shocking. And then they didn't stop there. They said, what if we now teach it how to play something else? And then from AlphaGo, they went to this Alpha Star to learn to play StarCraft. And it played against humans, and actually did very well against humans as well. So this was an incredible achievement, and people were wondering, oh my gosh, what's the next step? And today, indeed, especially now, you've seen ChatGPT, so I will not even ask this question. Do you think that a robot would pass the entrance exam for university? Indeed, just ChatGPT has been used to challenge an MBA exam and even medical license exams, and it passes all these exams. So I'm not going to ask this question. I'm going to skip it. I have an example. This is actually quite interesting, because when Watson beat the humans at Jeopardy, people found it fascinating and amazing. But when you open the box and see how it's done, so you lift the veil on the magic, then it's not magical anymore, and it's not as impressive. So this is an example of how, very crude example, high-level example, how Watson works to answer questions of Jeopardy. So the question is, Mozart's Last Symphony shares its name with this planet, and you're supposed to answer with a question. So what we do is this is a factoid question. We call it a factoid. It's not a yes/no question. You have to give a fact, and that fact is put in a question. So when I give this puzzle to the machine extracts the words that are relevant here. I have the word Mozart, the word last symphony. Okay, last symphony is important. Last is important, and symphony is important, and Mozart is important. Later, also planet will be important, but I'll take these ones and I simply search them online. And if I search them online, I get different results. I take one of them, for example, this one, a highly ranked one, Symphony number 44, because it has symphony in it, which is one of the important words, and it has Mozart. So I'll get that and I download it. Then I will read it. Actually, the computer doesn't read it. It scanned through it to try to find some of the words that are relevant. For example, symphony, Mozart, these are all the words that were in the original question. And in addition, I see if I can find something related to planets. And so words related to planets, I extract the planets from another page, Mercury, Venus, Earth, and whatever, and I can see that there is Jupiter here. So that's how I compose my answer, and I'll say, what is Jupiter? And there you go, I'm done. Okay, so when you see how it's done, the mechanics inside, it's not that smart. It didn't guess it by itself. This is to answer yes/no questions. I'm not going to go through it. It's actually quite simple because we don't have much time. But nevertheless, people are actually very worried about AI, and they're making a big fuss about it, that it's threatening. There's the machines that will eliminate us. So what do we do? And there are many organizations now that have been created to discuss this. I'm going to skip this, go quickly. But is it really a threat, or is just paranoia? And I showed you this example last time, that how computers can make very easily, they can make mistakes. Okay, I'm going to skip that. But this idea that computers could be a threat, so AI could be a threat, is not new. Even from the 60s and even the 50s, people thought about what will happen if these machines become as intelligent as humans. What scientists were saying, that we shouldn't disclose this possibility. It can happen. So what we have to do is we have to devote enough energy and thought about how to deal with this problem if it arises. We don't have to wait. We shouldn't wait till it happens. Here's the article that came today, the 2nd of February. This is in the Global Mail today, and they're talking about this AI posing an existential threat to humankind. So it doesn't stop. Each time there's an event like ChatGPT, like before that GPT-2, like before that whatever event, you have these articles. So this leads to this notion of singularity. So I don't know if you talked about it in the past. I'm looking at Dr. Solis. Have you talked about the singularity or not yet?
Yes, we have.
Okay. So the technological singularity, very briefly, since you've seen it, is this idea that at one point, computers will be at the same level as humans. If that is reached, then innovation will be run by computers, and they will self-improve they will have this self-improvement kind of loop, and eventually they will become more intelligent than humans. When that happens, you can't predict what will will come next. And that's basically the singularity is the moment where the computers take over for innovation to create new things and improve themselves. And it will happen at a very fast rate, to the point that we can't actually comprehend it. And I'm using, so people are skeptical. Some people are skeptical this will never happen, while others will say, no, it'll happen actually very quickly, faster than we think. So I use this metaphor to show that, yeah, it's very possible. And the metaphor is like this. You have a mouse, and this mouse, well, this mouse, if it needs to cross the river because the food is on the other side, it will do it. It'll swim. Okay. If it finds cheese, it'll eat cheese. Cheese is not part of its diet. It doesn't exist in nature. Humans created cheese, and now it'll eat it if it finds it. When it builds its nest, if it's in the field, it'll use what it finds to build the nest. But if that mouse is in my garage, it'll use artificial things from my garage, like paper and strings and plastic and whatever, to build its nest. So it's adapting to the world. It's to adapt to the world is actually using some kind of intelligence. If you put that mouse in a maze, it will learn that maze, and in the beginning it'll stumble on these walls, but after a while it'll actually know, and it'll go directly to the reward, that piece of cheese at the end. You can imagine that the mouse is able to do some very simple arithmetics, like my baby here and my baby here. Yeah, I have two babies. I have them all. And if one of the babies died, I had three, and now I have two. It can count. But can you imagine the mouse looking at the stars and thinking, are there other mice in other planets? Does it actually even realize that these holes in the sky are actually planets? When it's eating cheese, can it imagine that it's actually, you have proteins that are folding and things like that? Can it see it as very small? Can it see it very big, like the universe? When it's going in my garage and actually making its nest in my engine, in the car that is parked in the garage, it doesn't even know it's an engine. The only thing it knows, it's warm. And imagine this mouse is in Florida seeing this rocket being launched. Does it understand what it doesn't comprehend what that is? Imagine the mouse thinking about now more sophisticated math. I mean, we can't imagine that this mouse has an idea about our thinking and our imagination and our at our level of intelligence. The mouse will see us as a threat, as a predator that may kill it, but it doesn't understand that we are more powerful in terms of force, and we can kill it, but it doesn't understand that we have a different level of thinking. And if it knows that we are more powerful, maybe more intelligent, it cannot imagine that kind of what intelligence is that. So there is this level of, you can imagine a scale where the humans are intelligent, the mice are also intelligent. They can adapt to nature, they can cross the river, they can learn to build a nest with something else, and so they have intelligence, but they are less intelligent than us. They're sub-intelligent. And if we are at level 0, and these are in the negative side, who says that there's nothing on the positive side? There could be something more intelligent than us. And we, like the mouse, cannot imagine what is our intelligence. We are intelligent enough to realize that something could be more intelligent than us, but we cannot comprehend what kind of intelligence that could be. Okay. So we can't conceivably think that a mouse could comprehend our degree of intelligence. It's the same thing. We can imagine that something can exist, but we can't imagine what it is. Okay, so I talk about 4 paths to get to that level, this technological singularity. The typical one is, well, before even the typical one, we try to use biology or help biology to get there quickly, but that will take a long time to uh, uh, help evolution to evolve into something that is more intelligent. The other way is to create an artificial intelligence that will exceed human intelligence, but that also I'm well, it's possible, but I'm not sure it is the fastest way because even if you compare, for example, the very large language models, they're not doing reasoning. They're only learning about the language. And if you compare to our brain is not as big. And yet, even we know the language part, I mean, the part in the brain that is dealing with language is even smaller than that because our brain does so many other things. So we're still far away from that. The other possibility is to have what we call the cybernet singularity. So this is a mixture of the humans and the machine. So the humans and the machine put together, we can basically create an interface between us and the machine, and that new entity could become more intelligent than us. And then this is what also we call transhumanism movement. And then the final path is, I'm speculating, it's just a hypothesis, that we could have from a collection of many different things, a network of things, like the Internet of Things, some kind of consciousness, some kind of intelligence can rise. And the reason I'm saying this is because by observing, for example, as one example, some insects living in communities, and I have a picture here of, actually I have a video, but we don't have the time to watch it. When you look at how colonies of ants behave and what kind of intelligence they have is actually fascinating. But individual ants don't have that intelligence. So if you look at how the nest is built, how you have these highways in the nest and chambers where they store things, and they even have other insects, herds of insects that they feed, and they use their excrements and stuff like that. It's phenomenal. But individual ants don't have that intelligence, but the collective put together, they can have this intelligence to think about an architecture and so forth of the nest. So it is plausible that an intelligence could also rise out of a collection of smart tools that we are interconnecting together. So here I'm trying to focus on the, I think there's a chat here. Let me see, what's the question? Oh, I have to leave. Okay, too bad. Sorry, but I understand. What time is it actually? Oh, okay. So I want to focus on the third one because I believe is the fastest one. Well, this is a picture of Jean-Luc Picard from the Star Trek series, and here he was abducted by the Borg, and he was assimilated by the Borg, and the Borg are a race of people that assimilate different other races, and they take their technologies, and so here Jean-Luc Picard is the Borgs have added some components. I don't know how, there's some mechanical things or machines, anyways. It's a mixture of machines and human. The interesting thing is that, well, these cyborgs are already among us. They exist. Like we have people with prostheses, whether it's a fake eye or a fake hip or fake knee, or we are already there. And even at the University of Alberta, we are working on smart prosthetics for the arm or for the leg. And I believe Patrick Pilarski will come to this class and talk about his research on prosthetics. the cyborg is not necessarily a human to which you add machine parts. It can be a machine to which you add human parts, cells. And this has been done already too. There are some experiments showing how you can use cells from the rat brain, so neurons from the rat, and you can control a small robot to move left and right and so forth. The interesting thing is that because these cells don't last very long and they die, they took other cells and they repeat this experiment. And every single robot, even though it's the same robot, identical, well, it has a different kind of characteristics, different personality, and different. So they're personalized, which is quite personalized personalized to the cells of that rat. Quite interesting. So I talked to also about the on Tuesday about cochlear implant and how we have the bionicle eye, the bionic eye, and I talked about the smart contact lens. So I'm skipping here quickly. I also showed you how I showed you here how soon we will have some bionic eyes that have incredible zoom capabilities. I think I showed you this slide, so I'll go quickly here just to remind you how we were able to zoom in. This is another example where I'm not going to do the video, but high resolution cameras nowadays are incredible. And if I have them in my eye, my gosh, I will choose to become a cyborg. And the cyborg, this phenomenon, exists and is widely spread. People are doing incredible things on their own body because it's not regulated. This is an example of this is called body hacking. So they hack their own bodies to add things. These guys have added an RFID underneath the skin to be able to control doors or be identified in a machine, slot machine or something like that. These are other guys who put underneath their skin a detector for hotspots, Wi-Fi hotspots. And when a Wi-Fi hotspot is detected, there's an LED light that turns on. I mean, it's crazy, but people do all sorts of things. Here's another guy who actually inserted, you can see how this is not professionally done, but they inserted a hard drive underneath their skin to record what the camera is taking while they're walking around. So all the environment where they are is actually stored on a hard drive underneath their skin. And so there are all sorts of experiments done by humans but this is the beginning. And soon, basically, these smart prosthetics will be added not to people who just lost their limbs, but people who choose to change their hand or their arm or their eye or their nose or their ear or whatever because they want to, because these prosthetics are better than what nature gave us. And soon you'll have connections to the brain. There's a company, there are many companies that are working on that. So it's at the next turn. It's very, very soon. What do we do then? I typically stop here and ask and see if there are questions. No questions? Should I continue? What time is it now? Oh, we have a few minutes. I still have slides, but
Yeah, we have 15 minutes. Yeah.
okay. So if there are questions, I can take them now. Otherwise, I can continue. I'll take more questions later. Okay. So I wanted to talk about the this. Oh, this is another non-prosthetic. This is a wearable that is printed. The different sensors that people have been experimenting with. There are also tattoos and so forth. What I want to talk about is this idea of intelligent machines. This is, again, not new. People have been talking about intelligent machines since the beginning of the idea of AI, even before the term AI was created. In 1950, Alan Turing wrote an essay, a book, Computing Machinery and Intelligence, where he was talking about these intelligent machines. And he even conceived a test to check whether a machine is as intelligent as humans. And the test is now called the Turing test. And for a very long time, that was the standard to indeed detect whether a machine is as intelligent as a human or not. Today, we know it's not good enough, especially for those who are familiar now with ChatGPT. But for a long time, people worked on this. And they, so what is this test? This test is you have a machine or a human on one side, you don't know, and there's a curtain or a wall, and this entity, a human or a machine, is talking to a human on the other side. And the human is asking questions, and this entity on the other side is answering the questions. And if this human, the interrogator doesn't know and cannot know whether it is a machine or a human on the other side, and then if it is a machine, then the machine is intelligent as a human. Okay, does it make sense? Okay, so can a machine fake it and pretend to be a human to the point that the human on the other side cannot distinguish whether it is a human or a machine? Then the machine is smart. So people have been working on chat tools, because this is a chat, this is a discussion, a dialogue that is happening between a human and an entity on the other side. And so the first chatbots have been around since the 60s. So the first one is ELISA, done at MIT. And since then, people have been working on these. And the first chatbot already was very good, but it's based on rules. So you have different rules, and if there's no rule to apply, then it's very easy to detect that actually it's not a human. But this fascinated a lot of people, and there was a competition every year called the LABMP Prize. The LABMP Prize was organized by this rich guy who had money, and he said the first one who can fake it to pretending to be a human, but actually it is a machine, then I'll give $100,000 as a prize. And people started working on it. And I have some examples of these winners each year. Oops, what do I have here? This is some examples of the conversations, and you can see very quickly we realize it's dumb. I'll share these slides so you'll see them later. I'll try to go faster. This is Alice, another chatbot. And again, at one point you realize that it's really dumb. Here's Cleverbot. Oops. This is Cleverbot. Same thing, even though they win. So imagine those who didn't win, they're worse. And then finally, the prize ended because a few years ago, I don't remember exactly when, that was 2014, a team created a chatbot that was pretending to be a young person, 13-year-old boy from Ukraine. And so the judges actually were more indulgent, thinking, oh, it's just a 13-year-old, so it can make mistakes. And it's from Ukraine, so it doesn't know exactly what the context here. So they allowed some of the mistakes. And what happened is that 1/3 of the judges were not able to detect that it's actually a machine. And but still, it's really bad. So I'm going to skip all this because now all this is becoming obsolete with ChatGPT. ChatGPT has a different idea. ChatGPT, unlike all these chatbots that exist, ChatGPT is based on this predictive model, language model that predicts what is the next word. Okay. I'll see some examples. Oh yeah, some of the big problems with these chatbots is that they're not able to understand, for example, sarcasm or humor. Okay, humor is the most complex manifestation of intelligence in humans, and I don't know if anyone demonstrating that animals have this humor either. Probably they do, but It's definitely one of the signs of intelligence with humans, that what distinguishes us from animals. So I'm going to skip all this. These are some examples from ChatGPT. I mean, it's very impressive. Well, now when you look at the output of ChatGPT and you show it to a human that doesn't know that it's ChatGPT that did it, we can't know that it's coming from a machine. And this is actually creating many problems with plagiarism and with copying in exams and stuff like that, because we don't know it's coming from a machine. It's really, really, really good. But the machine doesn't understand it. The machine is not reasoning to create it. The machine is simply creating one word after the other based on some probabilities. And it gives you this amazing result because of the amazing size, the massive size of the network, and the humongous size of the training data, billions of documents. That's why we get these results. Okay, this is a summary just talking about the achievements. I'm going to skip this quickly. And yeah, I'll end here. I want to give you a chance at least to ask questions.
Yeah, I have a quick question. So when you were talking about the Turing test about with that 13-year-old boy, and you said, oh yeah, like it like since it's supposed to emulate a 13-year-old boy, judges kind of think like, oh, it's just a little kid, so they make mistakes, XYZ. But like that in itself kind of it insinuates like a flaw with the Turing test in the sense that the context of your machine actually totally varies the result. So
it's more, yeah, I agree, but it's more a flaw with the competition itself than the Turing test. So the LABMP guys, when they did that, I think they should have had these rules to avoid the cheating, because this is cheating basically. They said it's a little teenager who's coming from a foreign country, so yeah, they can make mistakes.
Got it.
Yeah.
No.
But I agree with you. It's also, it shows a flaw in the test itself. Yes. Yeah. But we know now, when you look at ChatGPT, I mean, nobody thought about ChatGPT at that time, and I can tell you that Alan Turing could not imagine something like ChatGPT. ChatGPT, you can ask it, hey, write me an essay in the style of a foreigner who's a teenager, and it can do that. And then you can say, write me an essay in the style of Shakespeare, and it'll do that.
Right.
So it's way more powerful than we thought.
So what are some more sophisticated forms of testing if if it's a human or a machine? Because I know there are programs now that can detect if text is generated by large language models. And I was just like, do you know how those actually works? Like I haven't looked into the methods behind those programs.
Yeah, so the program that detects, there are different programs that exist, GPT-0, and that was done by one person. And then recently, OpenAI released a program that detects also whether it's output from ChatGPT or not. And this is in response to the criticism from around the world, from the universities in particular. And some universities are now forbidding the use of ChatGPT and all that stuff because of the high risk of cheating by students. So OpenAI said, okay, here's a program that will detect with some accuracy. I mean, it's not 100% accurate, but in some accuracy, it will detect whether it is generated automatically or not. They were supposed to have what we call a watermark in the text, but they didn't do that. I don't know if they will do it in the future, so that we can easily detect whether it is easily between quotes. If you look between the lines, you will detect whether it's a machine or not. But currently what they did, they basically generated a lot of text from ChatGPT and used that as a learning test, learning data, so training data, and they build a machine learning technique, machine learning algorithm to detect whether it is ChatGPT or not. I don't know, their accuracy is in the 80 something or 90%, but it's not 100%. It still has false positives and false negatives. But what your question is, what is the test that will replace the Turing test? There's a lot of debate on that. What is sure now is that the Turing test is not enough. But what is the best test? There are many proposals, but there's no agreement yet for sure what is the best test to detect whether the machine is smart enough or not. What is smart is actually because there is something that you see, like the output of ChatGPT, and that gives you it gives you the illusion of intelligence. And then there is the reasoning that is happening. How did ChatGPT generate this output? This is like the Watson experiments. And I told you, we open the box, and once you see the magic, it's not magic anymore. Okay, the magician does a trick in front of you, it's fantastic. But once you know how they do it, it's not a big deal anymore. And it's the same thing right now. Currently, these amazing language models, even though they are, I mean, amazing, they're still dumb. They're still dumb. I mean, I have examples. I don't know if I showed you one example last time, but I have many examples, and you can find them online. Some are really, really stupid mistakes that a human would never do. But because there's no reasoning behind it, it's just probabilities, then it can make mistakes. Yeah. Did I address your question?
Yeah, totally. Yeah, no, that's all very interesting. Like like I'm in computer science, and we're introduced to the whole concept of Turing test, but yeah, this kind of makes me think about it a little deeper, and the future of testing programs and things like that. Yeah, thanks.
So ChatGPT now, they are combining it with other knowledge graphs like Wolfram Alpha. So these are knowledge graphs that allow you to do math, for example, because ChatGPT cannot do math. So when it detects it has to do with arithmetic and stuff, it will go to this knowledge graph. So people are trying to combine these. Same thing with Lambda. This is the language model that Google did. They actually have part of it that learns how to do arithmetic and how to, so it learns math. So it's not as dumb as ChatGPT, but it's still not doing any reasoning. So people are still trying to think about ways to combine what we call symbolic AI. Symbolic AI has been around for a long time. So since the 50s, when they started AI, they thought about logic, they thought about reasoning, how you prove a theorem, and so forth. But that's another branch that is different than deep learning. And some people are trying now to work on how to combine the two. So how can learning do, and we call it symbolic, neurosymbolic learning.
Right. So let's take the argument of I asked ChatGPT to solve a system of linear equations, right? So I ask it that, it detects it, it goes to Wolfram, whatever, and then I'm assuming Wolfram runs a preset algorithm that will solve these equations. But isn't that in itself reasoning? Because as a human, we recognize the problem.
Yeah.
And in a sense, we solve these problems by running algorithms in our head.
But
so
it's a programmed reasoning. So it's me, the programmer, that is programming this reasoning in the system. If you detect that there's a formulae or some arithmetic that you have to solve, then go and ask your helper, Wolfram Alpha. But it's not a reasoning that it's done by itself. And that's different.
Okay.
I have to head to my, so somebody's leaving, I
Okay,
guess.
so
Yeah.
I think that's the end of our time period. So anyway, thanks for another great session. And
Thank
look
you.
forward to next week. Yeah.
Okay. So
All
next
right.
week I'll be talking about machine learning.
Sounds good.
Awesome.
Yeah.